Here, and we're off. Welcome everyone to the free GRE Prep Hour. I'm Neil Thornton. I've been teaching the GRE for 20-something years, both live and in person and online. And let me talk a little bit about what the GRE Prep Hour is all about. This is our opportunity as instructors to get really granular, to get really specific on one aspect of the test. So we bounce from quant to verbal, or we might do two verbals or two quants. Today, I will talk about our subject matter today largely is out of the GRE. Oh, we'll talk about that. Our logic today is how to use something you learned in 4th grade, how to find factors and prime factors, and apply that to really, really difficult questions on the GRE. And Kritika, you asked a question. If you have general questions about the GRE, let's answer those after the session, but remind me of that question. That's a really good question. So, hi folks, for watching the recording. So, what we're covering today is we're going to talk about factors and multiples, how to deal with advanced questions with those, and then also how to apply those to more difficult, that skill to more difficult exponent rules. So that's our job today. If we have questions today, they're largely coming out of the Manhattan Prep GRE book, a 5-pound book of questions. Now, I love this book, but it's a really thick book, and it can be kind of, again, a little intimidating to look at. What I like to use the 5-pound book for in particular is to take a practice test on Manhattan Prep, or wherever you take a practice test, even the ones you get through the GRE program, GRE.org, the ETS exams, find out where my problem areas are, and then use the 5-pound book to fill in the blanks. So you take a test and you realize, oh, I need to work on percents. You can open up to the percents chapter and work on that. So you go to factors and divisibility, like today, you're going to open up that chapter and go from there. So mostly the chapters we're working on are divisibility and primes chapter, as well as the exponents chapter. So those are our chapters we're working out of, and that's the source of all of our questions today. So let's get going and ask two really, really basic questions that you will see in some form or another on the GRE, perhaps. So one of the things you might be asked are about the factors of 24. So in the chat windows, start bouncing out what are some of the factors of 24 for me. We'll start getting those on the screen and give you a methodology for getting those out. Okay, 1 in 24, 2 in 12. Okay, so notice we're getting these in various orders. So my general thing I like to do with the factors of 24 is I like to put these on my scratch paper, and if I'm asked the factors of 24, I'm going to set up a T-chart for myself. All right, so plain factors, factors, I'm going to do the T-chart. And in general, I'm going to start from the outside and work my way in as far as factors. So 1 times 24 equals 24. And then I'm going to use this left side to count up and try to be as systematic as I possibly can. All right, so that I don't miss anything. 1 in 24, 2 times 12, 3 times 8, 4 times 6, 5 times nothing. All right, I've already looped around. So here's my question. How many factors does 24 have? How many? Okay, so it's got 8 factors. Great. A question you might be asked is the word distinct. What do you think distinct means if I say how many distinct factors does 24 have? Okay, so different. So if I take something like, a perfect square, like 4 in and of itself, I've got 1 in 4 and 2 in 2. So how many distinct factors does 4 have? All right, so 3 distinct ones. So those are the factors of 24. This is something of a different question. We've got the prime factors of 24. What tool did you learn to use to get prime factors out? Oh yeah, all right, the factor tree. All right, so the prime factor tree. Depending on where you were educated in the world, there's different ways that this is taught, and I don't really care which method you use. But what I'm going to do is 24, and I'm going to pick 2 numbers that multiply equal 24. Let's take 3 and 8. 3 being prime, so I'm going to lock that one in. 8 is not prime, so I need to break that down a little bit further. So I get 2 times 4. For 8, 4 is not prime, so I get 2 times 2. So I get my prime factors over 24 are 2 times 2 times 2 times 3. Dumb question, but important. What happens when I multiply 2 times 2 times 2 times 3? What do I get? I get 24 again. Hey, this is for me shaking out the ingredients of a number. If I see any number, I go, all right, what are you made of, number? It's like I look at a cake I really like. Oh, how did you make this cake? What ingredients did you use to make this cake? How many cups of sugar? How many cups of flour? How many eggs did you use? How many, how many grams of butter did you use? So this is shaking out the ingredients of a cake to figure out what it's made of. Now, just to make a point, it doesn't matter. I use 3 and 8, but you could have used 2 and 12. And I go 12 is 2 and 6, and 6 is 2 and 3. And I get the same prime factors no matter how I shake it out. Other ways of rewriting 2 times 2 times 2 times 3. You can tighten this for exponent purposes down to 2 cubed times 3 if you want to, or if that's something that you're being asked about. Cool. What else do I want to say about that? All right, so that's shaking out the ingredients. This is tightening it up. This is putting it on our screen in some packaged way. All right, so how many prime factors does 24 have? Actually, I'm going to say the test writers won't probably ask it in the way I just asked it. So I'm going to say actually, as far as prime ingredients, 24 has 4 prime factors. How many? All right, so 4 prime factors, 2 of them are distinct prime factors. Great. So let's go and just answer a GRE question based on that. So I'm going to clean out, I'm going to clean off this page for us. You've done your notes, and I'm going to move to the next page. Cool. All right. And there we go. All right. Okay, so good question, folks. Let's go back here. Some definition type things. What do we know about prime numbers? What makes a prime number a prime number? What's your definition of prime? This is an awesome question, and I'm really, thank you, Samantha. So let's go back here. All right, so prime number is divisible by 1 and itself. So if I take a prime number like 7, how many factors does 7 have? All right, it has 2. So it is divisible by 1 and itself, and therefore it has 2 distinct factors. All right, so that makes a prime number a prime number. 2 factors, 1 and itself. So 2 distinct factors, 1 and itself. And I want to get that 2 factors here to help your memory. So let's take about the number 1. What are the factors of 1? 1. How many distinct factors does it have? 1. Does it fit my definition? All right. So we learned something new. Thank you. 1 is not prime. So we don't have to worry about that as a factor. That's an awesome question, by the way. So that might be news to you. And it is a hard rule on the GRE. So 1 is not prime, and therefore we don't have to consider it as a prime factor. So when I've broken out the prime factorization of 24 as 3 times 2 times 2 times 2, only 3 and 2 count as the distinct prime factors. Awesome question. Well done. All right, so let's move on to the next screen. So I want to go to an actual GRE question, and we'll come back to, we're going to go to an actual GRE question here. Number 3. So here's one out of the 5-pound book for us, and we can play with that. So the number of distinct factors of 10 versus the number of distinct prime factors of 210. So what's the difference in language we have to pay attention to? What word popped up in one that didn't pop up in the other? All right, so distinct, but distinct prime. So we want to separate out the 2 skills. So do I use, So we've got two skills. We've got our tree, but we've also got our t. So the tree or the t. So on number 3, on the left side, quantity A, do I use the t or do I use the tree? Okay, so I want to set this up as the T. For those of you brand new to the GRE, I'll cover this kind of question here in a moment, and other people who have been studying can help us out with this. So let's work out the T on 10. All right, so work out the T on 10. So what can you multiply to equal 10? Well, 1 and 10, 2 and 5. So how many distinct factors does 10 have? All right, so it's got 4. All right, so column A is give me 4 distinct factors. All right, so the number of distinct prime factors of 210, what tool do I use, tree or T? Use the tree, excellent. All right, so let's break it on down. Here we go, so I'm gonna go 21 times 10, because that makes sense to me. 21 is 3 and 7. 10 is 2 and 5. So how many distinct prime factors does 210 have? All right, so we got 4. So let's run through the potential answers here. Now notice I didn't put the answers on because before you go take the GRE, you need to memorize the 4 possible answers to this kind of question. This is called quantitative comparison. So those of you doing your study, there are 4 answers, possibly A, B, C, and D, that you can click. What does answer choice A mean? You pick A if what is the case? A is greater. All right. So if A is greater, we're going to pick quantity A. All right. We would pick B, why? All right. If B is greater, great. Why would you pick C? All right. If they're always equal, no matter what, so they're always equal to each other. And D means what? Yeah, it cannot be determined from the information given. I like to think of D as it depends. D for depends, as in it depends on what I plug in. If I plug in one thing, I get A, another thing I get B, another thing I get C. So cannot determine based on what I've plugged in. So I like A is always greater, B is always greater, C that means they're always equal, D means it depends. So what's our answer to this one? I got 4 on the left, 4 on the right. What do you got? All right. So there you go, C. So a little practice and familiarity can get you through the answers on these. The answers are always listed on the screen, but you can save a little bit of time and effort if you have those memorized. Yay. All right, so we got the language of an actual GRE style question, distinct factors, distinct prime factors. There we go. All right, so we're going to get nitpicky, and we're going to use this to help ourselves get a lot more advanced here. So I'm going to play around with what we can do with a number. All right, so when I see a number and like 48, or I see it on a license plate, I've been doing this long enough that my brain just starts going, oh, what are the ingredients of 48? All right, so 48 is 6 times 8, and a 6 gives me a 2 and a 3, and an 8 I've just memorized as 2 times 2 times 2. So I know 48 is made of 4 2s and a 3. So that's the ingredients of a 48. Now let's take out and let's play with the plain old factors of 48 for a second. This is an interesting thing that occurs, and so I got 1 and 48, 2 and 24, 3 and what? 16. Check this out. 3 times what equals 48? Well, if I look here, notice 2 times 2 times 2 times 3, 2 times 2 times 2. Shoot. All right, I'd advanced before I wanted to. Let me go back a little bit. There we go. All right. I got 2 times 2 times 2 times 3 equals 48. Well, one of the ways you can figure out the other factor is I know it's 3 times all of this, and 2 times 2 times 2 is 16. So it would be 4 times, well, everything else that's left. 2 times 2 times 3 is 12. 5 and nothing, 6 and 8, and I've wrapped around. All right. Let's talk about some language here of divisibility and multiples. We called 12 a what of 48? Factor or multiple? Okay, so 12 is a factor of 48. Therefore, 48 is a what of 12? It's a multiple of 12. So we'll work out some mnemonics for getting that language right. But what does this mean to me in manipulation and moving a lot faster on the GRE? All right, so product of 12. If I take 48 and I break it out to its prime factors, so if I say 48 divided by 12, and I put this, say if I'm asked what is 48 divided by 12 or some big number divided by some other big number, I get something like 48 and I break it out to its prime factors, 2, 2, 2, 2, and 3. And I break out 12 to its prime factors. Real quick, do that for me. What are the prime factors of 12? Okay, so 2, 2, and 3. So I've set this up as a division problem. Now I've broken out into its little component pieces. What do you notice? What happens to those 2s and those 3s? Oh, they cancel out. So this is kind of gazinta, right? 12 goes into 48. 12 is a factor of 48. Why? Well, because all the ingredients you need to make a 12 are in there in that 48, that 2, that 2, that 3. So I look at when I'm thinking about factors and multiples, I think about that 48 as like my kitchen pantry. It's where all the ingredients I might want to make a cake are in that pantry. So I got 4 2s and a 3 available to me to use. And what can I make out of that? Well, as far as the factors that are available to me to make that 48, I have 2 2s. I can make a 4. I have a 2 and a 3. I can make a 6. I have 3 2s. I can make an 8. I have a 2, and a 3. I can make a 12. I have a 2, and a 2, and a 2. I can make a 16. So all the questions that 12 is part of 48, is a piece of 48. That's a great question, Vanessa. All right, so if it's a part of 48, if you can use the ingredients of a 48 to make a 12, well then 12 is a factor of 48. 8 is a factor of 48. It divides, it goes into. So what I can do therefore, as I go, so this is fun, I'm advancing even though I don't want to. What I can do then is I can use that to actually make things that, let me see if I've got an example. There we go. I can make what look like relatively unwieldy division problems or factoring problems actually kind of easier for me to process mentally. So if I've got a problem like 36 times 24 times 21 100 divided by 6 times 10 times 14 times 9, my instinct is to get out my calculator and go 36 times 24 times 21 times 100. But that might not be the fastest way of going about things. What I'm going to do, and this is not actually what I would do, I'm going to do this twice. But if I can think of a 36 as far as its ingredients, like I know 36 is a 6 and a 6. So a 36 is actually a 2 and a 3 and a 2 and a 3. There's my 36. 24 I know is a 2, a 2, a 2, and a 3. 21 is a 3 and a 7. And what's 100? All right, I'll go off to the side and do 100 is 10 times 10. Oh, a 100 is 2 and a 5 and a 2 and a 5. All right, so what do I got? I got 2, 3, 2, 3, 2, 2, 2, 3, 3, 7, 2, 5, 2, 5. This seems unwieldy, but helps me understand what all of this is made of, what all of this is broken out into. So I know a 16 is 2, 2, 2, 2. Why? Experience and practice, folks. 16 is a 4 and a 4, and that is 2, 2, and 2, 2. You can take the time and do it, and then learn it. 10 is a 2 and a 5, a 14 is a 2 and a 7, and then a 9 is a 3 and a 3. What have I set myself up to be able to do now? Okay, so I know all sorts of canceling can happen. So let's get rid of 4 2s on the bottom, and then 4 2s on top. 1, 2, 3, 4. I'm going to go to left and right. I've got a 2 and a 5, so I'll get rid of a 2 and a 5 here and a 2 and a 5 here. I've got a 2 and a 7 to get rid of, a 2 and a 7 and a 2 and a 7, and then I got 2 3s to get rid of, so 2 3s here and 2 3s here. And if I'm careful and systematic about it, I can see that all I'm left with here is, if I'm right, 3 times 3 times 2 times 5, and that's all I have left with. All right, so done all of my canceling, and now I've got ultimately 90 left over. It takes a lot less brain capacity if I haven't actually multiplied anything out. Now, if I'm going to do this for real on my own test, will I expand everything out like this? No, but I will keep in mind what expanding out would require for me. So what I might do on my actual test is, knowing that some of the ingredients, like, oh, 21 and 14 have a 7 in common, so I'll take a 7 out of this one and I'll have a 2 left over, and a 7 out of this one and have a 3 left over. 10 and 100 have a lot in common, so I'll pull out a 10 out of that one and be left with a 10 here. And I can systematically reduce and be clear that my reducing is better because I know what 24 and 21 are made up of. Give me a yes or no if this is making sense and why I'm doing this. All right. So rather than building up, we're breaking things down to its pieces. Like, say somebody tasks you with, oh, look, you got to move your actual house across the street, right? You don't have the physical capacity to pick up a house, but if you got a ply bar and a nail and a hammer, and we're able to start ripping the parts apart, taking it apart, you could probably slowly and carefully move that house across the street in its little pieces. Everything is easier to manage mentally if you break it down. That's all. That's our point. So let's keep going and see where we are. All right, so I'm going to clear this off and go to some other kind of interesting questions based on these components. All right, so now I'm going to think about, let's go back here and making sure I got some of my language here. All right, so in here, let's start working, making sure I got my language right. Mnemonics. Factors are few, multiples are many. Factors are the little things, multiples are the big things, mostly. 1 is a factor of everything, but 30 is a multiple of 30, you know the drill. But, so factors are few, multiples are many. Just making sure you got your language set. So why don't we, if your name starts with an A through an E, do the first one. If your name starts with a G through a L, do the second one. M's and N's, if you'll do the third one, and R's, S's, and beyond, if you do the fourth one. Type it out using the numbers 5 and 30. So is 30 a factor of 5, or is 5 a factor of 30? Is 30 a multiple of 5, or is 5 a multiple of 30? Which way does it go? All right. Good. All right. So you got the right idea here. So let me just fill these in for you. All right. So 5 is few. So 5 is a factor of 30, but 30 is a multiple of 5. 30 is divisible by 5. 5 is a divisor of 30. So we learned that factor and divisor mean exactly the same thing to the GRE test writers. And ultimately, 30 divided by 5 is your integer. So getting your language straight and realizing, oh, this is just different language to describe exactly the same thing. I get it. Great. Okay, moving forward. Where do I want to go next? So we did our factors. Let's move forward a little bit. All right, to things like least common multiple, greatest common factor, and what do we 30 over 5 is an integer. All right, so which of the following makes an integer? Well, if I take 30 divided by 5, comes out clean, does it not? Yeah. What is 30 divided by 5, folks? 6. Okay. So that means this is another way that things are expressed on the GRE. So let me just show you the example of that. Blank over blank is an integer, means that 5 is a factor of 30, 30 is a multiple of 5. All right. So one of the ways our test writer deals with this concept is by asking questions that look like this. For how many positive integer values of x is 65 over x is an integer? So what is that really asking about x? It's another way of phrasing exactly this question using some of the language we've talked about. This is something I've seen actually on the GRE. So x would be a what of 65 in this case? Yeah, okay, so this is another way of saying how many divisors does 65 have? How many factors does 65 have? So how many positive integer values of x is 65 over x an integer? It's just, oh, okay, they're just basically asking how many factors of 65. So you can rock out 1 over 65, 2, no. What in 13? 5 and 13. I think it ends up being 4 here. All right, so you break out and if you want, you can break out 65 to its prime factors, and that will help you out. So 65 is 5 times 13. So how many prime factors? 2. How many factors? 5. Why? Well, because 65 over 1 is an integer. 65 over 65 is an integer. 65 over 5 is an integer. 65 over 13 is an integer. All right. So there we go. Just same question, same concept, different language. That's all. All right, moving to the next thing. One of the things that you get asked in very peculiar ways is you generally don't get asked in this language is LCM GCF questions. You got to ask this in school, but the test will often ask you this concept in funky ways. All right. LCM stands for what? Those of you who had this in 4th grade. Least common multiple, and GCF stands for greatest common factor. All right. So what we're doing all the time today is we're breaking these numbers out into their component pieces. So do me a favor, let's prime factor out 18 and see what we get. What do you get when you prime factor out 18? Excellent. All right. So I got 2 times 9, and 9 is 3 times 3. All right. So 18 is a 2 and a 3 and a 3. All right. So leave that alone. Go for 30 for me. All right. So we get a 5 and a 2 and a 3 to make a 30. All right. So let's talk about common factors. What ingredients do 18 and 30 have in common? 2 times 3. All right. So you can see that 18 and 30 have a 2 and a 3 in common, and a 2 and a 3. So 2 times 3, that would be what? A factor or a multiple? Okay. All right. Factors are few, multiples are many. So if it's smaller, it's a factor. All right. So there you go. So it's just getting the language sorted out in your head. All right, so what 2 times 3 is, it's the greatest common factor. It's the biggest one that 18 and 30 have in common. I can take a 6 out of an 18, and I can take a 6 out of a 30. All right, so 3 would be the greatest common prime factor. So the whole factor overall would be 6. And you can work this out also if you wanted to do, 1 and 18, 2 and 9, 3 and 6, and you do 30 over here, 1 and 30, 2 and 15, 3 and 10, 5 and 6, and you see, oh, the greatest one they have in common is 6. But to shorten that process, I can expand these out into its pieces and go, oh, there's a 2 and a 3 in common. All right, so the GCF here, the greatest common factor, is 6. What other common factors do they have besides 6? 3, 2, what else? There's one common factor. How? 1 is a factor, but it's not what? It's not prime. Okay. So anything I can make with a 2 and a 3 and a 1, these would be factors of 18 and factors of 30. So 2 would be a factor, 3 would be a factor, 6 would be a factor, 1 would be a factor. And you can see that on our list. 1, 2, and 3, and 6. 1, 2, 3, and 6. All right. So that's greatest common factor. All right. Least common multiple. Well, let's build a multiple of 18. And let's see. So we're trying to get a common multiple. And we're going to do this with a bit of a shortcut, but I just want to show you kind of thinking about this. All right. To make an 18, what are the ingredients I need to make an 18? All right, I need a 2, a 3, and a 3. Sweet. Okay, so I got a 2 and a 3 and a 3 to make an 18. So in my multiple, I could multiply this by all kinds of other stuff. Anything else, any other integer, and I'd have a multiple of 18. As long as I got a 2, a 3, and a 3, I could add a 7, and that would be 7 times 18, or I could add a 2, and that would be 36. But any multiple of 18, I got a 2, a 3, and a 3. So as long as it's got these ingredients, I know I have a multiple of 18. Let's move over and think about a 30. So what do I need to make a 30? 5, a 2, and a 3. So in this pantry over here, what do I already have? Down here on this multiple thing over here. So I need a 2, a 3, and a 5. I already have a 2 and a 3. So if I put only a 5 in here, look at what I've made. What is 2 times 3 times 3 times 5 anyway? Oh, it's 90. All right, cool. So by getting a 2, a 3, and a 3, I have enough ingredients to make what? An 18. To put a 2, a 3, and a 5, I have the minimum ingredients to make 30. So the least common multiple is what? Multiple, yeah, 2 times 3 times 3 times 5, which is 90. All right. Multiples are many, bigger. Multiples are bigger. All right. Factors are few. All right. So Danielle, you gave me a factor. All right. So multiples are many. All right. So you can shortcut this process, by the way. You start here, you break out your 18 and your 30, but you can actually do a little Venn diagram trick to make these work for yourself by drawing 2 circles over here to the left. Put an 18 above this one, 30 above this one. What did we say they had in common? Two and a 3. So if I put a 2 and a 3 in here, I know 18 needs a 2 and a 3, and I know a 30 needs a 2 and a 3. So off here to the left-hand side of things, I'm going to put what else I need to make an 18 that I haven't put there already. So I need another 3. So notice 3 times 2 times 3. That'll give me my 18. All right. On that other side, that 30 side, I am going to put everything I need to make that 30 that I don't already have. So 2 times 3 times 5 makes that 30. All right, so if I look across here, hopefully I can do this without advancing the slide. In this group, 2, 3, 2, 3, I've got enough to make my 18. On the right-hand side, 2, 3, 5, I've got enough to make my 30. All right, so what have I created for myself? Well, I made a nice little Venn diagram. And 2 times 3 is the what? LCM or GCF? Okay. So 2 times 3, if I multiply those together, I'll get my GCF. And if I take all of these, 3, 2, 3, 5, and multiply those together, so the greatest common factor is 6. But if I go 3 times 2 times 3 times 5, I'll get 90, and that's my LCM. Cool. All right. So this is a little shortcut that is useful and helpful if that's the question you're being asked, but it can also help us. This, just simply looking at the spotlight, this plus this little box of what do I need, what do I not need, can help us with some more really interesting advanced questions, and we'll play with those a little bit. But yeah, that Venn diagram, if you want to rock out LCM and GCF of 180 and 15 or 15 and 18, it doesn't take you that long to do, right? And if that's something that you're being asked to do, not so bad. So let's see if we can find one where I am being asked to do that particular question. All right. So smiley faces so far, everything cool? Having fun? All right, good. All right. Excellent. So let's see if we can find a question. All right. So least common multiple of 22 and 6, greatest common factor of 66 and 19. So this is rare, but we're just being explicitly asked to rock out LCM and GCF. All right. Multiple, big thing or small thing? Big thing. Factor, big thing or small thing? All right. So this is just, if you want, you know what, I'll just take a second and I'll just twiddle my thumbs for like 30 seconds while you start the process here. And a question, what is the first tool you should be using to start playing with this? You see 22, you see 6. What do you do? Yeah, find your prime factors. Yeah. So get your prime factors out is the first thing. So 22 is 2 and 11. 6 is 2 and a 3. All right. So LCM, GCF, let's use that tool I just had. What do these two have in common? 2, so we'll rock that in the middle. 22 needs an 11. 6 needs a 3. Multiply those together. What do I get? 66. All right, so the least common multiple of 22 and 6 is 66. And if you want to double check that while you're working your homework, go for it. You're 22, 44, 66. So those are your multiples of 22. Multiples of 6 are 6, 12, 24, 6, 12. 18, 24, 30, blah, 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 60, and 66. All right. So the first common multiple you run into is going to be 66. All right, GCF, greatest common factor. All right, what are the ingredients of a 66? Good job, Simba. All right, so we got a 2 and a 3 and an 11, and a 99 is going to be a 3 and a 3 and an 11. So what factors do they have in common? Cool. 3 and 11. So the greatest common factor is going to be 33. All right, what column is bigger? A, B, C, or D? Cool. So A is greater, B is greater, C means they're equal, so A for A. Awesome. All right, so that's if you're being asked that. Now, more common in the GRE is to be asked the concept, but not the exact language that you're used to. And so when we get this language of multiples and whatnot, it can be a little bit, A, confusing, B, intimidating. Just realize it's the same concept being asked in potentially somewhat tricky language, but the tools remain the same. The kind of problem solving you need remains exactly the same here. So let's go through and I'll show you kind of more, to me, a more common kinds of questions that you might ask. All right, so n is divisible by 14 and 3. Which of the following statements must be true? All right, so let's build a block. So notice they didn't say LCM, GCF, any of those things. But let's start building a little box of what do we know about n. So if n is divisible by 14, what do you know? What ingredients is it going to have? All right, so we know it's got to have a 2 and a 7. But it's also divisible by 3, which means you know for sure it's also got a what in it? All right, so it's got a 3. Now, it might have some other crap. It might have a 5, it might have a 15, it might have other things, but I know for sure n has got a 2 and a 7 and a 3 in it. Cool. So 12 is a factor of n, 21 is a factor of n is a multiple of 42. Interesting. So I have broken out 14 into 2 and 7 and 3, and I've put that, so I know this is n. These are the ingredients of n. How do you make a 12? What do you need to make a 12? 3 and a 4, all the way down to prime factors. Okay. So 2 times 2 times 3. Do I know for sure all of those ingredients are there in n? No. Okay. Good. So that's not our answer. Could be. Doesn't have to be. All right. I need 2 2s. What about a 21? What do I need to make a 21? Oh, I need a 7 and 3. Are all the necessary ingredients in there? Why, yes, they are. So that's one of our answers I'm going to click on. What do you need to make a 42? What are the prime factors you need to make a 42? Okay, so I need a 7 and a 2 and a 3. Hey, do I have all those ingredients? Hey, how cool is that? All right. So this is just, it's the same tool, prime factor tree. Break it all out and you can start answering these questions. Why not 12? What do you need to make a 12, Avantika? How many 2s do you need to make a 12? All right, so I need 2 2s and a 3. N might have has 1 2, a 7 and a 3. So if I go back up here, the question is must be true. Does this have to have 2 2s in it? Does n have to have 2 2s in it? Does n have to have 2 2s in it? How many 2s does n clearly have? Just the 1. Okay, right. So it's got the 1 2, at least 1. It might have another 2 in it, but must be true. Does it have to be divisible by 12? Nope. And you can look at that. What is 42 times 7 times 3 is 42. 42 divided by 12. Does that come out evenly? No, it does not. All right. All right. So you can test it out with your calculator. You see it comes out with a funky decimal. What would that decimal be? Yeah, I'm not sure. Doesn't matter. Okay. Here we go. All right. So this is the whole thing of like necessary ingredients versus what's actually there. So if in order to make my cake, I need 2 eggs. We've talked about this a little bit before, but if in order to make my cake, I need 2 eggs and a cup of flour, this one I have, let me go back one. Oh, I'm ahead of myself, sorry. I'm going to come back yeah. So if I need 2 eggs and a cup of flour, I've only got 1 egg in my pantry. I can't make my cake. All right. So let's move on and go on to one that is peculiar, and then I'll show some exponent rules. So what's the one that I wanted to show you all? I load in about 7 hours worth of questions because I'm greedy and if I can show as much as I can. All right, so K is a multiple of 24, but not a multiple of 16. So this goes more to really what happens on the GRE is they're playing with this common multiple thing, but then they're messing with me, but it is, but it isn't. All right, so if K is a multiple of 24, what ingredients do you know it has? Excellent. So I know it's got 2 times 2 times 2 times 3. All right, great. So I know it's got 3 2s and 1 3. But it is not a multiple of 16. Well, if it were, what are the ingredients of 16? So So there's a weird little restriction. So 16 is made of 4 2s. So what have we just learned about K? It is a multiple of 24, but it's not a multiple of 16. Oh, I know it is a multiple of 3, right? So these are the ingredients I know for sure about K here, right? K has got 3 2s and a 3 in it. And it is divisible by 3, Shruti, you're right. It is divisible by 3 here. It doesn't have 4 2s. All right. So we've just learned a lesson and we know something about this if we have only 2 times 2 times 2, not 4 of them. There's only 3 2s. All right. So now they're asking which of the following cannot be an integer. Well, K, I know, has 2, a 2, a 2, and a 3, and anything else except for what? Another 2. All right. So I can start playing with this. I'm going to actually clean up this 24 here and start playing with, I know K can have any other things in it except for one more 2. So if I start playing with this and I say K, 2 times 2 times 2 times 3 times anything but a 2 over 8, which is 2 times 2 times 2, can I do that? Yes or no? Is that going to work out? Yes, it is. All right, so let's put a yes next to A. What about B? And B is a little bit tricky. I have 2 times 2 times 2 times 3 over 9, which is 3 times 3. Could that maybe be a thing? Because we said K could have anything else but a what? But a 2. All right, so maybe if I change that, I'm going to change my little color here. Maybe if I add another 3, that doesn't violate my rules yet. All right, I can add that 3, but I can't put another 2 in there. All right, interesting. All right, so let me change that back to blue and we'll come back to that. All right, K, 2 times 2 times 2 times 3 over, and anything else but a 2, and 32 is what? 2 times 2 times 2 times, 2 times 2. Can I do that? Nope, not allowed to have 4 2s. We've broken the rules. All right, so I might have another 3, but I can't have another 2. So there's my no. What's my answer going to be? All right, C. All right, and we can keep playing. 2 times 2 times 3 dot dot dot, and 36 is 2 times 2 times 3 times 3. Yeah, that's cool. I could pop another 3 in there, but I can't pop another 2. And K, 81 is made of a 3, a 3, a 3, and a 3. So I can have a boatload of 3s. I just can't have 4 2s. All right. Why is C the answer? Well, what is the question? Can or cannot? Melissa. Okay, so cannot be an integer. All right, so people in the chat window. I know people watching the recording can't see the chat window. Sorry. And I will read it out to you. What? Explain to me why C cannot be true. I can't have more than 3 2s. It has a fourth 2. 32, because it has 4 2s, is divisible by what? Is divisible by 16. What does the rule say? Not a multiple of 16. So a little technique trick, when I'm building these little boxes about K, if I put a variable up here and I say what are the ingredients it has to have, and then I'll put a little dot, 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 dot here to indicate that could be, I don't know what else it's got in it, but I know for sure In this case, if it has another 2, it's illegal because it cannot be a multiple of 16. This, if you're not 100% there now, don't worry about it. This is something that it's a tool, this prime factor tree, that will aid your understanding. So you go into the 5-pound book and you play with a bunch of these. There's a bunch of these in the actual official guide that I highly recommend you play with. And you break these out and you start experimenting with, well, what do you know about perfect squares? How many prime factors do they have, and what happens? What are the building blocks? And oh wait, what is factor? What is multiple? It takes time and it takes practice to master a lot of this, but I'm just giving you a tool to start with that you can then understand. So this is 5-pound book, divisible multiples chapter, question number 14. Go play, have fun. All right, let's wrap it up with one thing of moving this on to someplace that it might not be expected, where this skill can be helpful to you. So if I'm being faced with a question regarding, say, now exponents, like say something 25 to the 7th power versus 5 to the 15th power, exponent problems can be used to help you compare exponents and see what's going on with exponents. If the base here is not prime, what I often like to do is take things that are not prime in exponents and break them down to their prime factors. So what are the ingredients of a 25? 5 times 5. Excellent. So how can I rewrite 5 times 5 in exponent terms? Yeah, 5 squared. All right, so I write 5 squared like that. All right. So what I've got, let me actually change that a little bit. All right, I'm going to erase that. Okay, I'm going to do this a little bit more tightly. So 25 is right, or we can rewrite as 5 squared, and I'm taking all of that to the 7th power. Now, in our classes, we're going to learn some hardcore exponent rules. Those of you who've been doing your studying, 5 squared to the 7th power, how many 5s do you end up with? I end up with 14 5s. All right, 5 to the 14th power. And actually, you can rewrite that, by the way. If you want to keep going with the exponents, it's 5 squared 7 times. So 5 times 5, that's second time, that's the third time, that's the fourth time, that's the fifth time, that's the sixth time, that's the seventh time. You can win and dot expand it out, and you'll see that you have 14 5s. And then I can compare that to 5 to the 15th power a lot more easily. Hey, which column is bigger? Column A, column B, they equal. What do you got? All right, so column B. All right. So if I take, say, 2 to the 16 is 2 to the x, 3 to the y, and this is a primary skill, I'm going to go, oh, this is a factor tree time here. All right, so 216, that's divisible by 3. So 216 is 3 times what? Calculators out if you need to, but 3 times 72, great. 72, I know, is 9 times 8. 9 is 3 times 3. 8 is 2 times 2 times 2. All right, 2 or 4, and then 2 times 2 times 2. All right, so what do we end up with? We end up with 3 3s and 2 2s. All right, so 3 times 3 times 3, that one, and that one, and then 2 2s times 2 times 2 times 2. Great. So that would be 2 to the what power? All right, 2 to the 3rd power, 3 to the 3rd power, and x and y are integers. So that x must be a 3, that y must be a 3. So I got 3 over here, 3 over here. Hey, what's my answer? They're the same, so answer choice C. All right. So again, same tool, prime factor tree, just helps me figure out what it's all made of. Great. Cool, smiley faces? Having fun? All right, good. And it's a funny, it's, as I said, it's one of my favorite tools. Every time I turn a birthday, I'm like, all right, am I prime? Am I not prime? When I turned 36, I knew the prime factors of my age. Last year, I was 47, no prime factors. Turning 48 this year, okay, 2 2 2, 2 3. So I can, it's a skill I begin to acquire and it becomes sort of automatic habit, and it just helps me take awful things and make them less awful, especially on the GRE. So let's go here. All right. Ooh, pretty. What? Yeah, when in doubt, expand. Well, when in doubt, prime factor. When in doubt, expand it out. Especially when you have ugly numbers. Okay. All right. So these negative exponents, what do they mean again? This may be a bit advanced for some folks. Yeah, 1 over or go below. So when I see this on the screen, here's a cute little shortcut. Anything that is negative exponent, I'm going to move when I recopy it down to the other side and make it not negative. So when I recopy this, the things that stay the same are going to be 25th to the 7th times 2 to the 16th. But that 10 to the 8th is going to go down below. It's 1 over, which means the 1 would be on top, the 10 to the 8th would be below. And again, we got 20 to the 6th power, and then I got 8 to the negative 1. Well, that's going to go up here, up to the top. So anything that's negative, you can kind of make them not negative and move them to the other side of the fraction pretty easily. All right, now sorting this out, because some are prime bases, some are not. Well, all right, what's the 25 made of? 5 times 5. All right, so I'm going to rewrite that 25 to the 7th as 5 squared to the 7th power. 2 to the 16th is already prime. 8 is also known as what in the exponent world? All right, 2 cubed. All right, 2 cubed, sweet. All right, now 10 to the 8th. So watch this. So if I've got 10 to the 8th, 10 is 2 times 5. So 10 to the 8th is going to be 2 times 5, all of it to the 8th. Then I can, what process with that? How else can I write that? All right, yeah. I can rewrite this as 2 to the 8th and 5 to the 8th. I can expand that out. Because what have I got? I got 8 2s. I got 8 5s, and you can rearrange those any way you want. All right, so I can rewrite that as 2 to the 8th times 5 to the 8th. All right, and then 20. What is 20? Is 2 times 2 times 5. So 20 to the 6, I can write as 2 squared times 5, all of that to the 6th power. So 2 squared to the 6th power is how many 2s? All right, so that'll be 2 to the 12th, and then 5 to the 6th. So if I take this out, take the top, and I'm going to move this down here. Up top, I have 14 5s. And then how many 2s overall? I got 16 2s, and then I got 3 2s. So how many 2s up top? All right, so that is 2 to the 19th power. Great. And down below, how many 5s do I have total? All right, I got 14 5s. And how many 2s ultimately? 22s? Yeah, okay. 2 to the 20th. Excellent. Hey, now I've sorted this out to its prime bases just using that little factor tree and understanding how these things, and also like it helps me process what's happening with exponent rules. Even if in my brain I expand out, all right, 5 to the 8th is 5, 5, 5, 5, 5, 5, 5, 5 to the 6th is, and so I can see 8 5s and then 6 5s, and oh, okay, that's only 14 5s. So having expanded it out on whiteboards and screens and scratch paper for the last 20 years helps the vision process of, and you can do the same. 1 week of you expanding this stuff out on paper, you can think about it a lot more cleanly and make a lot fewer mistakes. All right, so 5 to the 14s cancel out. 19 2s cancel out, leaving me with a 1 up here and a 2 down here, leaving me with which answer overall? Hey, 1/2, also known as B. Excellent. All right, so when in doubt, break it out. That's our rule of the day, how the prime factor tree works, how our language works of multiples and divisibility and factors, as well as how this can be a massive both brain saver and time saver on test day. Faced with a big number, one of my primary tools is to make it not so intimidating. I see 210. I don't want to deal with 210. Let me break it down into its pieces. So there we go. That's a free prep hour for today. People watching YouTube, happy to have you show up live. People who are here at the moment and or watching YouTube, want to do a quick moment of giving you some thoughts. Those of you who are just now coming to the GRE, one of my recommendations to you is the following. To get a big overview of the GRE overall, the question types, how to manage, how to study, how to think about pacing, class 1 of any one of our classes is free to you, and we do a big overview on the GRE. So first session of any course is free, so go to manhattanprep.com/GRE's classes. There's live ones in New York and other major cities in London. There's also online ones. We also have an interact lesson as well, which is a self-study program with all sorts of cool videos of all of us bantering about the GRE. My next course that's coming up for you, I'm going to actually take a moment and put in the chat window for you. It is called Live Online Fall G, and it's on Monday evenings starting September 24th. So Live Online Fall G is the next one that I'm teaching online. Look forward to seeing you there. So you were awesome today. Thank you for the trial class is the first free class. And other than that, people watching on YouTube, hang out, come see us live, come and we'll see you soon. All right, I'm going to turn off the recording. Otherwise, goodbye. Have a lovely day. The rest of you can split, and I will stick around for a question or two. Bye.